In this question, sulfur trioxide reacts to form sulfur dioxide gas and oxygen gas. This reaction happens in a rigid vessel in equilibrium at 950 Kelvin as represented by the equation. The partial pressure of gases at equilibrium are shown, so I already have the pressures at equilibrium. Calculate the value of the equilibrium constant Kp for the reaction at 950 degree Kelvin and write your answer using two significant figures. To find the value of the Kp, all I have to do is write the balanced equation and then write the pressures. The pressure of the product, which is the pressure of sulfur dioxide, and this is raised to the power of 2 as the coefficient of sulfur dioxide is 2, multiplied by the pressure of oxygen, and this raised to the power of 1 because the coefficient is 1. I'll after that divide this by the pressures for the sulfur trioxide, which is the reactant, so SO3, and this again to the power of 2 because the coefficient is 2. After that, I will just have to put the numbers in the table. So I will write sulfur dioxide is 0.50. Be careful while copying the numbers, and this is power of 2, and then multiply the pressure of oxygen, which is 0.62, and then dividing this by the partial pressure of the reactant. So I have here 1.4. We just write 1.4 for sulfur trioxide, and this raised to the power of 2. Now let me get my calculator and do it. This will be equivalent to 0.079, and we know that it has no unit. In this question, I have here a reaction at equilibrium at 298 degree Kelvin. The concentration of bromine and chlorine gases under these conditions are 0.015 molar and 0.050 molar, respectively, given that equilibrium constant Kc is already found out to be equal to 7.8 at 298. Find the concentration of BrCl in the equilibrium mixture. So in order to find out the concentration of BrCl in the equilibrium mixture, let's first write the balanced equation. So balanced equation telling us that Kc is equal to BrCl because this is our product, and this is raised to the power of 2 because the coefficient is 2, and then divide this by the reactant, which is Br2 to the power of 1 multiplied by Cl2 to the power of 1. After that, let's put just the numbers in the problem and solve for the BrCl. So I will just say that 7.8 is equivalent to, let's give some space. So 7.8 is equal to the BrCl2, which is required to find, divided by the multiplication of Br2, which I have it is 0.015, multiplied by the Cl2, is a 0.050. So here it is the same like the previous questions, only the difference is that I have the Kc and one of the concentrations is not there. So I will just say that the BrCl2 is equal to the multiplication of these two, which is 7.8 multiplied by the 0.015 and 0.050, and this one is squared. So if you don't want the squared, you just have to give the radical of this one. So the radical will be found from the radical of this one, and in the calculator will give me the answer as 0.076. This is a missing one. If you square this one again and divide it by these two, you will get 7.8 if you want to double check the answer is correct. In this question, 5 mole sample of X gas and 6 mole sample of gas Z are combined in a rigid evacuated 1 liter container at particular temperature, and the reaction represented above occurs when the mixture reaches equilibrium. I have 1 mole of R represented in the container. What is the value of the equilibrium constant? So in order to find the value of the equilibrium constant Kc, we must find the concentrations at the equilibrium. If you are given the concentrations in something which is not in equilibrium, like in the initial reactant, then you have to find that initial the concentrations at equilibrium by the ice table. So let's write the equation Kc is equal to Q, which is our product concentration, multiplied by or to the power of 2, because this is coefficient 2, multiplied by R, and then we'll divide this by the reactants. I have X multiplied by Y, and both of them raised to the power of 1. For starting, the text tells us that 1 mole of R is present in 1 liter container at equilibrium, so R is equal to 1 mole. Next, since 1 mole of both X and Z is consumed for every 1 mole of R, we know that 4 moles of X and 5 moles of Z must remain in the container, so is X equal to 4 and Z is equal to 5. If this is difficult for you, you will know the importance of the ice table now. So the X and Z reacts to form 2Q and R. If you make the ice table, this will be very simple because you have 5 moles of X reacted with 6 moles of Z in the container at a particular temperature, and the reaction presented when the mixture reaches equilibrium. 1 mole of R is present. So I have here 1 mole. Why did I put this in this row? Because this is the equilibrium row, because the reaction has finished and reached equilibrium. He wrote here it's reached equilibrium. So this 5 plus and 6, both of them will decrease by a value. I don't know the value. I don't want to write X here. So I will write minus A and minus A. And this one will increase. It will become plus. But is it A or 2A? It will become 2A. But why it will be 2A? Because the ratio is 1 to 2. So the ratio is 1 to 2 to 1. So this one decreases by A and this decreases by A. This increases by 2A. I just used A instead of X because X is already in the equation. Then I will write plus 1A. This is the change. If this initially was 0 and this was initially 0, because he didn't mention anything about adding Q or R at initially, and 0 has become A, so this means that I know A is equal to 1, because it was 0 and become 1. So what is the change? 1 minus 0 is 1, so A is equal to 1. So this change is 1. So 5 minus 1, how did you know it's 1? Because A is 1. So 5 minus 1 is 4. Initially it was 5 and it became 4. And 6 minus 1 is 5. And the Q has increased by 2A. So it was 0 and it will become 2. And this one was 0. This is the one we used. So I can just plug in my numbers. I can say that Q, which is equal to the concentrations at equilibrium again. I will never use anything in the QC or the QP other than the equilibrium concentrations. This one. So Q is 2 to the power of 2 and R is 1 to the power of 1 divided by X, which is 4, and Y is equal to 5. Can write it here in the same way so we don't change, but both are correct. And then I will get my answer equal to 0.20 just by the calculator. This is the correct answer. In the next question, the solid carbon reacts with carbon dioxide to form carbon monoxide. This reaction is at equilibrium, and the student places samples of carbon and carbon dioxide into previously evacuated rigid vessel and then heats the vessel to 1000 and 100 and 1010 Kelvin. The system is allowed to reach equilibrium, at which point some carbon still remains in the container. If the partial pressures of carbon monoxide, so let's write the equation. This is carbon solid and carbon dioxide give us 2 carbon monoxide gases. Very important to put the physical states, and we'll know why now. So to find the partial pressure, we first use the balanced equation to write out our expression. Expression is Kp is equal to the pressure of the product, which is PCO, and this is power 2 because the coefficient is 2, divided by the pressure of, do we use the carbon? No, we don't use the carbon because the carbon is solid here, This is solid carbon, and any solid we cannot mention or liquid in the equation. So I will just write the carbon dioxide pressure, which is raised to the power of 1, and the coefficient is equal to 1. So I have the Kp, and Kp is equal to 3, and I have the carbon monoxide pressure, which is 3. So I need the partial pressure of carbon dioxide. So partial pressure of carbon dioxide is equal to the partial pressure of carbon monoxide squared divided by Kb. I just switched these two together, and that's equal to the 3 squared. This is the pressure of the carbon monoxide divided by the Kb, which is equal to constant, says here 2. And this will be equivalent to 4.5. Take care, we are not measuring or calculating the Kb, we are calculating the partial pressure, so we need a unit that's atmosphere. The reaction system represented above. At equilibrium at 475 Kelvin, the concentration of carbon monoxide gas under these conditions are 0.205 and 0.130 molar respectively, given that the equilibrium constant is given already pKc equal to 47.4 at this temperature. Find the concentration of CH3OH in the equilibrium mixture. So to find the concentration, we need to use the Brownian equation to write out the expression for the constant Kc is equal to the concentration of CH3OH, the methanol over the concentration of the products, which is carbon monoxide, multiplied by the hydrogen, and this is raised to the power of 2. We are very good at that now, and that's equal. So if I want CH3OH, let's get the value of CH3OH equal to the cross multiplication value. So that's equal to the Kc multiplied by the concentration of carbon monoxide multiplied by the concentration of H2 to the power of 2. So I will say 47.4, this is the Kc value, multiplied by 0.025, this is the value given, sorry, 0.205, this is the value given, 0.205, given for the carbon monoxide, and multiplied by 0.130 squared. This is a value given for hydrogen, but it is squared. So I will get the answer equal to 0.164 molar. This question, 6 mole sample of X and 6 mole sample of Y are combined in a rigid evacuated 1 liter container at a particular temperature. Every time I have 1 liter here, it makes things very easy because the concentration is equal to the number of moles divided by the volume, which is 1, so it's equal to the number of moles already. So if X reacted with Y to form 2 moles of Z and 1 mole of Q, and I have started with this number of moles, 6 moles here, sample of X, and 6 moles sample of Y. He didn't tell me that I started with anything with the Z or Q. And so this is the initial concentrations, and I need to find the change and the equilibrium concentrations. He has given me one of the equilibrium concentrations, luckily for the Q equal to 5 after the equation has reached the equilibrium rate. So I don't know what will be here because I don't know what is the amount decreased and what is the amount decreased here, but I know that this started with 0 and this started with 0, and I don't know what is the increase here, but I know for sure that this one has increased by 5. It was 0 initially and become 5, so I know that this is equal to 5. So plus X here is ratio is not plus X. Just look at the ratio. This is 1 minus X and minus X, and this is 2X. Why this is 2X? Because the ratio is 1 to 2. So look here at the numbers. The ratio is 1 to 2 and 2. So we have to follow the ratios. So let's determine the equilibrium concentration for the 4 gases. This is equal to 5. Since 1 mole of both X and Y is consumed, for every mole of Q, we know that 1 mole of each of X and Y must remain in the container. 2 moles of Z is formed for every 1 mole of Q. The vessel must contain 10 mole of Z at the equilibrium. Again, if it is difficult to understand like that, you'll see what's the importance of the ice table. It makes things very easy for you, and you put the numbers in front of you and don't get confused. So this is increased by 2. Why this increased by 2? Because the ratio is 2 here. And this has increased by 1 only because the ratio is 1. So it is 1 here. So I know that x now is equal to 5. Why is that? Because 0 has increased by x and become 5. So this x, which is the increase, is 5. So x is equal to 5. 6 has decreased by 5, so it is 1. 6 decreased by 5 is 1. And 0 has increased by 2 x's, so it becomes 10. Why it's 10? Because 5 multiplied by 2 is 10. Now the equilibrium concentrations, I can just write my expression. Expression says that Kc is equal to the z to the power of 2 and multiplied by q over the x to the power of 1 and y to the power of 1. So z to the power of 2 is 10 to the power of 2 multiplied by 5, and this is divided by 1 multiplied by 1. So 10 to the power of 2 multiplied by 5, that's equal to 500, and this is my answer in the required number of significant figures.